Hi, welcome to second part of 10th video series about neural networks. In this video, we'll be going through one step execution of backward propagation. So, if you look in our previous video, we were able to calculate how much should we change the gradient or how much should we backpropagate each of the gradient value to the previous layer by invoking the backward function defined in each of the operations, like backward function, add operation, multiplication, tan h, etc. Now, this is good to start with. In this node, we just have these many inputs, so we are able to assign everything, and we're just able to manually type everything as backward, and hence able to let me run everything, and hence able to update our graph, update our network. But this is not really feasible because we can't keep calling every backward function that we define in a particular sequence for hundreds or thousands of nodes or weights. So in order to so in this video, we will create one single function, which when invoked will update all the weights across the whole network. In order to do that, we need to go and execute this network in a specific sequential manner. So we start with O, which is output, and then we go one layer back, which is N. And then we go one layer back, which is X1, W1, X2, W2, and also B. Since nothing is related to B, since B is a constant here, its backward gradient update will be 0. So the B is going to end here. And the X1, W1, X2, W2 should be taken a step back to X1, W1, which we created here, and then X2, W2, which we created here. So this is the sequence we need to follow to backpropagate and upgrade weights. So whenever O dot backward is invoked, N dot grad is updated. The gradient at N is updated. The same way, when N dot backward is introduced, the B dot gradient is updated, as well as the gradient of X1, W1, X2, W2. So we need to go in this reverse fashion to update the weights, and this should always be in this sequential flow. We can't update X2, W2 until we update all the gradients in the next layers of X2, W2. So this essentially means we need to follow a graph. And one of the graphs that is used to create this backward propagation in an automatic fashion is a topology. So I'll go through this code. I'll type this code and then go through on how are we building this graph. Now visited is set, it's an empty set, and let's define a recursive function known as build topology, which takes a node maybe V, and if V is not in visited, that is not in the list, then we are going to add V to the list. For child in V dot previous, that is essentially okay. I'll explain the code later, but let me just fill up the information here. So for child in v.previous, we need to invoke the same function with the child as input instead of v. And let's keep appending the output of this function, this recursive function in topo. And that's it. This is a simple function, and we can call this upon O. Perfect. Now, so when O dot grad is equals to 1, that essentially means, and then we need to invoke this function. And okay, even before going there, let's try to understand what this function is doing. So as I've said, we need to go through in a backward fashion for each of these weights in our network. This can be done in multiple ways. Maybe we can start a path by this way. This is path 1. And then we can do another path here. This is path. Okay, we can do another path in this way. This is path 2. And then another path in this way. This is path 3. So basically, a topology helps to write all these graphs in a sequential manner. So let me print something to debug, and then it gets easier to understand. So in this topology function that we created, we initialize this with O. We call the O first, and it will just save. So we need to go through each of this node only once. So there could be a network where X to W2 could also be input to B. What if there's also some kind of multiplication here? That means this flow as well as this flow, both of them will go through X to W2. And we should not update the weights twice in one iteration, right? We can't really calculate the gradient twice in one iteration. That's the reason why we are creating a set saying in every iteration, we need to go through each element only once. So we are starting with O. And is O present in this empty set? No. So if it's not present, then we are going to add it to this empty set saying we are looping through O. And then what is pref? It's basically O dot underscore previous. So just to go back and recall or refresh our memory, previous is another default argument that we have set up in this class, and it contains what are all the aspects that are present in the previous layer. So for O, the only thing that comes as an input from previous layer is N, while N goes through some activation function to get to O, but the input for O is basically from N. Hence, O underscore previous contains N, right? Cool. Now, so that is our child here. That means we started from O, we went back to N, and now we are starting from N, which is our child, and we go back to X1, W1, X2, W2, and B, right? So let me print some debugging statements so that it will be easy for us to follow this recursion. So print, let's do child of, so this is our input V, and the child of our input is basically child dot label. So whatever is present in previous of V, that means whatever is present in the before layer, we are just trying to print its label, and whatever is present in our current layer, we're just trying to print its label. Now, as I've said, for O it is N, and for N it is two things, x1 w1 x2 w2 and B. So if we look here, we have child of N is x1 w1 plus x2 w2, that is correct, and child of N is B. Now, why didn't it print x1 w1 x2 w2 and B after each other? Because we are going through a for loop. This is where the recursion aspect comes in. So the first element that is going into the child is x1 w1 x2 w2, right? So it started with O, and for the O the child is N. So it started with N, and for N there are two childs because this is the addition operation. And the first child here is x1 w1 x2 w2. Hence, we got the child of N is x1 w1 plus x2 w2. And this is now the input, and this acts as V. So x1 w1 x2 w2 is now V. And for x1 w1 x2 w2, there are again two childs, x1 w1 and x2 w2. So the child of x1 w1 x2 w2 is now x2 w2. This is the first element that is present in the way that we defined the data. And now in x2 w2, again it's a multiplication factor of x2 as well as w2. So the child of x2 w2 is going to be x2 and w2. So the first element that went into is w2, and then there is no child for w2. Hence, it gets terminated here, and then now this is done. The sequence is done. Let me draw it for us. So this sequence is done. Now there's another child that is x2. So this sequence starts, right? So that's why we see the child of x2 w2 is x2. So with this, the whole aspect of x2 w2 is done. Now it goes to the second input of x1 w1 and x2 w2, that is x1 w1. So this is where it is, and it repeats the same process. For x1 w1, there are two inputs. One is x1, the other is w1, and hence it just goes through these childs, and then even this part is completed. Now let me delete everything and show you something. So we started with N, which backpropagated to x1 w1 x2 w2, and we finished all of the graph before it. Now for N, there's B that should also be taken care of, and now the B is invoked, and hence we are seeing B to be executed at the end. So I hope you are able to follow this. To summarize it on a high level, we need to do backward propagation. And in order to do backward propagation, we need to write a function which goes through all of the nodes in one way. It starts from 0, it goes to N, it might go to B, and then again it starts from N, it will go to the other input x1 w1 and x2 w2, and then it splits down further and it splits down further. So in this way, we start from O and we go all the way back to the input nodes. That exactly is being happened here. And the order of linked aspects is important. Like the order of doing N and then doing any of this is fine. Any of the X1, W1, X2, W2 or B is fine. But we should never do N and then go back directly to X1, W1 or X2, W2. Because X1, W1 and X2, W2 rely on the gradients of X1, W1, X2, W2. Because of that, if this is not calculated, then we can't calculate its previous layers gradients, and that's how a network breaks. Wonderful. So this is done. Now if we just print topo, we could see that the value is actually, it starts, instead of starting it from O will be your last element, and then N will be the last second element, and so on. So O is 0.7, N is 0.88, and then we have -6. Okay, we have beta value 6.88, and then we have -6, and so on. This happened because we are using recursion, and in recursion, it works on a stacking mechanism. FIFO, first in, first out. So hence we started with O, but O is at the last stage. That's the reason why we need to reverse it. Now for node in reversed of topo, we can just call the function that we define, and let me execute everything for you so that it's clear. Oh, so we no longer need this backpropagation aspect here, because we now created a function to backpropagate. So let me actually delete these two, and you would see in our first forward loop we have all the forward paths calculated and the gradients are 0. Now after executing this one, we start with O.grad to be 1, and then we go back, and we can see that with initialization of this function, we're able to calculate the same gradients with just one single call. Now let's update this into the main class value that we created, and this can be done by creating a new function known as backward. We're going to initialize this with an empty list. Instead of we are going to actually input this. We can input this as v, and we'll remove this print statement, and we need to append v, that is right. So we start with O. We call this backward function on O. So O is going to be the self, and it starts here. And once this is done, we'll have this list of topo, and the gradient that we're going to start with, the final layer is 1. And for node in topo, we need to reverse it, right? Reverse topo. We just need to call the individual backward aspects that we define for every operation. So it's simple node dot backward. And we have 0 gradients, and now all that we need to do is just call backward on O, and we'll see that the gradients are updated. So this basically concludes our backpropagation, both mathematically and in terms of execution wise. I hope you are able to follow this, and feel free to reach out to me for any questions. And again, all we did was, instead of calling this backward functions individually on each of these nodes, we created a graph where we keep track of the nodes in a sequential manner and just call the individual backward functions on them. Wonderful. I'll catch you in the next video. Take care. Peace out. Bye.